We are going to go through some questions where we have to determine the set of points at which the function that is given is continuous, and we are focusing our attention on multivariable functions. Okay, so before we even look at the examples, it's very important that we understand the theory of continuity of a function in general, whether it's functions of independent variables, functions of two variables, or perhaps functions of three variables. It's very important that we understand where what we mean when we're talking about that particular function being continuous. Okay, one thing that really stands out when it comes to continuity of a given function, or let me say of any function, is the fact that the function is only continuous at its domain. Okay, the function is only continuous at its domain. You can't have a function that is continuous at a set of points that is not within its domain. That doesn't really make sense. That it doesn't just add up. It doesn't make sense. Okay, so so let's say let me give this example. Let's say you have a function f of x is equals to 1 over let me say 2 minus x. Okay, so this is a rational function, and this function is going to be continuous, we said, on its domain. And how do we get the domain of this function? We focus our attention on the denominator, but this is only the case because of the how the function is. It could have been a different case where maybe if I had like a natural log on top, maybe natural log of x, or perhaps it was something like maybe I put x with a root there like that, such as a radical. But because I just have something that is as straightforward as just having a value such as 1 on the numerator, then on the denominator I have a value and a variable which is x. So the denominator is one that's where is one that is going to help me to find the domain for this particular one, because looking at the way it is here, it's more like let's say we had x on the numerator. Okay, I wouldn't really care what the numerator is, whether it's zero, negative, or positive. I don't really mind. Okay, so what I focus on in the is the denominator, unless if maybe the numerator was something like a radical or a natural log, because we know those have limitations. Okay, so meaning I know that for my denominator it's not supposed to be zero, so I'm saying my 2 minus x should not be what? Should not be 0. So what I'm simply saying is that my x should not be what? Should not be 2. So what it means is that the domain of this function is like, if I were to put it in interval notation, you are starting from as low as negative infinity to positive 2. Okay, then you are starting from 2 again. um, you're starting from 2 to what? To positive infinity. Okay, so this is the domain of this function. It's going to be continuous on that domain. What does it mean? It basically means when you draw the graph, you're going to have an asymptote at positive 2. Okay, so this is the domain of this function, and that is where it's going to be what? It's going to be continuous. So if someone was to ask you for the set of points at which this function is continuous, just determine the domain, then um, you would have found that those particular set of points that you are looking for. Okay, and it also helps sometimes to try to graph to give you a picture of what you're really talking about. So the first example that I'm going to look at is let me say f of x f of xy there is equals to, let me say it's e to the x minus y. So this is an exponential function. Okay, and when it comes to exponential functions and looking at what I have here on the as the power, um, I don't really care what it is, because it can be a negative, it can be a positive. Okay, it can be zero. I don't really care. Like, I can have a negative there, I can have a zero, and I can also have a what? I can also have a positive. If I have a negative, what it simply means is more like, let's say you have e to the negative 1. What this is just 1 over what? 1 over e. If you have 0, e to the 0 is simply what? Is simply a 1. If you have e to the positive number, let me say 1, this is going to give you e, which is 2.71828 and some values. It keeps on going just like that. So one thing that it really tells me again here is that no matter what value that I replace there, what I'm going to get is always a positive. So it basically means for the domain Okay, for the domain is just a set of points from negative infinity to positive infinity. You can pick any value that you want. The only thing that's limited is the range. The range is starting from, I would say, starting from zero to what um, starting from zero to what to infinity. But the question is that, are we including zero? um, in this case, I would say yes and no, in the sense that the the let's say the smaller the power gets, the closer you get to what the closer you get to zero. Okay, so it's more like it's approaching zero, but it's not really reaching zero, so we'll do that. So what I mean is this: if you have, let's say you have e to the negative 100, okay, this is simply like 1 over e to the power 100, like that. Okay, this value is very very small, so it's like as this one is getting smaller and smaller and smaller, at some point you have like e to the negative 1000, and it will just be, it will be approaching zero. It's more like you're trying to determine the limit of that, as you're trying to determine the limit of that, and you observe to say if you are approaching negative infinity, or as this one is getting smaller, um this value approaches what approaches zero. So simply, this is a domain. We can say the domain is what from negative infinity to positive infinity, and this happens to be the set of points where that function is continuous. So what I would want to do is that I would want to try to use a graph, so that we try to have a picture of what we're really talking about here. Okay, so let's try to say, okay, we have our f x comma y, that is equals to e, okay, e to the x minus y minus y, and this is how the graph is appearing. Okay, so what we observe is that in the what I have here, my this red part, okay, let me do that. So this one is my x-axis, this one is my y-axis, and this one is my z-axis. So one thing that you observe is when it comes to the surface, what I mean is the x and the y. Okay, this is getting closer, this graph is getting closer and closer to what, closer and closer to zero. But what it really tells us is that we are picking any value that we want in the x, and any value that we want in the what, in the y, either positive or negative. But for the z, we cannot go on the negative side, so I mean, like, we can't go below here. The graph is just up here, it's heading towards what, towards positive infinity. That's for the range. But for the domain, you just look at your surface, which is your x and your y planes, and that's really that's simply how the graph is appearing there. Okay, so let's try to look at another example. We try to understand this a little further. So let's say we have our f of x, f of xy being equals to tan inverse, okay, tan inverse of x over y. So what it is here is that this can accept any values. Okay, the only thing that's difference is that in what quadrant is it, positive or negative. But I don't want to really waste my time on that, because I'm just looking for the domain, because the domain is simply the one that tells me the that tells me about the continuity of that particular, of this particular function. So what it is that looking at what I have here, this is a rational expression, so this can be anything but what, it can be anything. All right, but we should just make sure to say our x is not what, is not zero. So it's just a set of points besides what, x being equals to what, being equals to zero. So it's more like starting from negative infinity to zero, union from zero to what, to positive infinity. Okay, that is for the what, for the x part. So once again, this can be anything, but we should just make sure to say, as we substitute, our x should not be zero, because that would be undefined. It's more like you're saying 1 over 0, which is simply what, undefined, or another way is infinity. Okay, so that's one thing that we are trying to avoid. So even if we graph that, we're going to have once again, this I simply say this one, it just all depends on, like, the inverse of tan. It's just that it's positive in some quadrants, it's negative in some quadrants, but that's not really our that's not really our focus right now. Our focus is just talking about the domain, but I'll try to graph this anyway so that we have a picture of how it looks like. So let me try to erase that. So we have our f, um, that's x comma y, that's equals to, I'll write as arctan of x over y, I mean y over x, and that's simply how the graph appears. Okay, so it's just about in which quadrant is it positive, but it's just a set of points, but our x should not be what? Our x should not be 0. Remember, the red arrow is for the x-axis, the green arrow is or the green line in short, like this is our x, our y, and our z there. Okay, so that's simply how the graph appears. So for that one, we just had to we just had to remind ourselves that our x should not be what? Should not be 0 for this to be defined, because um, the domain is simply a set of points at which your given function is defined. So now let's talk about another one. Let's say our f of xy is equals to uh, natural log of 1 plus x squared plus y squared. We close like that. So one thing that we understand about natural logs is that here we are not supposed to have a negative, and we're not supposed to have a 0. What I simply mean is that, for example, let me give these three examples. I'm going to get a negative number, 0, as well as a positive number, so that we try to make sense out of this. So if we say ln of, let's say 0, no, let me start with negative 1. Then let me say ln of what? 0. And say ln of what? Positive 1. So here negative 1 is representing all the negative numbers, 0 is just representing itself, our 1 is representing all the positive numbers, all the positive real numbers in short. So what does this mean? One way in which I like simplifying this for myself to understand this better is that I know that ln is simply log base e. So we are talking about log base e of 1 is equals to what? What is it equals to? Okay, so even here saying log base e of 0 is equals to what? We don't know. So here saying log base e of 1 is equals to, what do we have here? Okay, so what it simply means is that what should we raise e to? So we're going to say e to the, in fact, let me do this. Let me use some variables here, maybe to make a bit sense. Let me say we have n m, we have n m, as well as let me say we have x here. Okay, so what it means here is that we are saying our e to the n. Okay, even here we say the same. We have like e to the m. Even here we have like e to the x. So now we are asking ourselves to say, what should n be for this to be negative 1, or what should m be for this to be 0, or what should x be for e to be what? To be 1. So what you observe is that there is no number that, like, there's no such a number whereby, like, we can't really say it's 0, we can't really say it's negative, because this number is always, the e is always positive. Okay, whether you raise it to like a negative, it's going to be positive, because that's simply like 1 over that same number, which is the e. So these, we are looking for a number such that if we raise e to that number, it gives us negative 1, and there's no such number. Hence, that's why we are not supposed to have a negative there. So what about this part? It's all the same. What can be m? What can you raise e to such that your answer is going to be 0? There is no such a number. So even that's why we disqualify that. So for this one, we're asking ourselves, what should x be for e to be 1? It's simply a 0 there. Okay, and it's the same pattern for when it comes to any other positive number. So it's more like you just be raising e to some numbers for you to get whatever that you're given here. For example, if I was looking for 2, I could have raised e to something such that whatever answer that I get there should be what? Should be a 2. So that's really one thing that we have to understand about what? About natural logs. Okay, so whatever that we have in the brackets here should be positive, okay, and should not be a 0. So that the narrative only changes if you are dealing with what, the modulus of that number that you have. So meaning you don't really care what you get besides zero. You can get a negative, but the negative sign is going to be taken care of by the modulus there. Okay. So what it means here is that our domain um, our domain is just since looking at, we are just dealing with brackets, we're not dealing with modulus. It's just a set of numbers from what, um, starting from zero to what, starting from 0 to positive infinity. Okay, that's our set of numbers. But again, on a second thought, we can easily ask ourselves to say, oh, okay, if we say it's from 0 to positive infinity, meaning we neglect all the negatives. That is true, but I would say it's partially true, because what I observe here is that even if I substitute with a negative number there, I'm going to get a positive. Even if I substitute with a negative number there, I'm going to get a positive. So what it means is that there is no chance of me getting anything that is negative there, because of the way my nature of x and my nature of y. Because whatever that we get, we square it. If it's positive, it still remains positive. If it's negative, it becomes positive. Okay, so what we observe here is that, and it's really interesting, is that we can never get a negative. No matter what we do, we can never get a negative. Okay, so meaning the only value that we are supposed to avoid for the domain is zero. Okay, what do I mean by a zero here? Mm, if if we say we avoid a zero, again, this kind of rings a bell. I'm like, okay, if the only number that I'm avoiding is a zero, is it possible for me to get a zero for this part? The answer is no. So like when you're talking about the negative part, in fact, I think that's one of the important things the questions that we have to be asking ourselves when you're talking about natural logs, is that, is there a possibility of me having a negative in the expression that I have? In this case, we said no, we can't get a negative no matter what we do. What about zero? Okay, is there a possibility of us getting a zero? We think of it again. We can't subtract here, and unless if maybe it was something like 1 maybe minus x squared plus y squared, I would say perhaps there's a possibility of me getting a 0. Let's just say x squared is equals to what, 1 plus y squared, meaning I'm going to get a 0. Alright, so in this case, looking at what we have, if our x squared, let me say, if our x squared is equals to 0 and my y squared is also equals to 0, so it basically means what I'm going to have is what, is a 1, which is something that is really, it's okay for me to get a 1, it doesn't really matter anyway. So we can't get a 0 even here. No, we can't get a 0. So what it means is that we can pick any number. We can pick a 0, we can pick a negative, we can pick a positive. So all the domain is just from negative infinity to positive what, to positive infinity. And I believe this is going to make more sense when we try to graph this. Let's try to see how this is going to appear. Okay, so we have like ln of we have plus 1 plus x squared plus y squared. Okay, here's what we have. That's how the graph is appearing. So what it tells us that, since we know this is our, when you look at it from the top, it covers all values of x, covers all values of y, because like this is the, this is like the plan of this. Okay, that's the plan. So you observe to say this side is the negative, okay, negative of y. This side is the positive of y. This side is the positive of x. We have negative of what? Negative of x. So meaning we can pick any value in the negative of y, negative of x. What about in the z? Okay, what about in the z? So the z is more like the outcome of our input from the surface, which is our xy. Okay, so what you observe is that remember we said the domain the domain is a set of numbers like from negative infinity to positive infinity. These are the numbers that we pick in the xy plane, like this surface that we have down here. We can pick any number. It can be a positive, it can be negative in terms of x and y. But what we get here is that we observe to say the lowest we can get for the natural log, that natural log that we have there, x squared plus I mean x squared plus y squared, like that. The lowest we can get is a what? Is a 0. What do I mean by it being a 0? Because if I put 0 here and I put 0, what I'm going to get is I'm going to get ln of what? Ln of 1, which is simply like we know to say ln of 1 is equals to what? Is equals to 0. So that's the lowest we can get. No matter what we do, that's the lowest we can get, and the highest we can get is what? Is infinity. So it's like you're saying 0 comma what? Comma positive infinity. That's our range. But for the domain, that's the domain that we have there, and that's simply the range of points at which that function is continuous. Once again, the function is only continuous at its given domain. Okay, so that's simply how the graph appears, like that. So let's try to look at the last example in this tutorial. So we have our f of xy is equals to in fact this has three variables. So y comma z is equals to 1 over um, x squared plus y squared plus z squared plus minus 1 there. So this is very straightforward, I believe, because all you have to do is that, okay, this is a rational expression. Okay, you just focus your attention on the denominator, because that is one that's the one that defines the domain. So the denominator is simply x squared plus y squared plus z squared minus 1. So this is more like a sphere of radius 1. Okay, so you're just saying, okay, my x squared plus y squared plus z squared minus 1 should not be what? 0. That's on the denominator. So no matter what we do, we should make sure to say this thing, what we have here, is not a 1. Okay, so we are saying our x squared plus y squared plus z squared should not be what? Should not be positive 1. Okay, and that's simply the domain. So it's like we can pick any value. It can be any value. The set of points is any value besides a 1, beside the sum of those numbers, giving you what? Giving you a 1. And that's simply how we go about answering those questions. It's just a matter of us remembering to say a function is only continuous at its given domain. So that's all in this video. Thank you very much for watching.